Okay. Today I'd like to give a presentation on current sensor design. I know it's a bit of an off-topic in power electronics, yet I think it's a very important building block to design in our power electronics converters. Specifically today, I will present then the current sensor that is based on the Planar Rogowski Coil. I've outlined the presentation as following. So first I'll give a quick introduction and background and get everyone up to speed on what a Rogowski coil is. Then we'll dive into the operating principles of the Planar Rogowski Coil, following that up then with the current sensor design itself. Then, of course, we have tested the sensor, and I'll show then the experimental results. And then lastly, I'll conclude the presentation with a couple of notes. If we dive right into the Rogowski coil itself, the Rogowski coil was first proposed by the German scientists Rogowski and Steinhaus in 1912, so it's over 100 years old, the technology. The idea is that a current carrying trace induces a magnetic field around it. And if we place then a coil around that current carrying trace, we can measure or it induces a voltage if the current changes. And the equation depicts that, where we have the mutual inductance, which is the coupling between the current carrying trace and the Rogowski coil itself. And then, of course, we have the IDT, the change in current. As we don't want to use the derivative of the current, we have to use an integrator then to get then an output voltage that is dependent then on the mutual inductance and the current through the current carrying trace. For simplicity, we'll continue then using the current electric circuit, where we have then our current carrying trace that couples then to the Rogowski coil with the mutual inductance, and then we have the integrator circuit. The benefits of using a Rogowski coil as a current sensor is that they can have a very high bandwidth for up to more than 100 megahertz. They can have a very small footprint, and as they don't use a core, it's an air core, so it won't saturate. There's a great linearity over the whole sensor's bandwidth. And the applications so far are for protection circuits, for wide bandgap devices. We can use them to measure switched transient currents, and also then to reconstruct the AC current. CPES has done a good amount of work on Rogowski coils, or PCB-based Rogowski coils, where what I'm showing here is a gate driver with integrated Rogowski coils, where then each Rogowski coil, so we have two Rogowski coils within the gate driver, and one Rogowski coil couples then to the DC plus of our half bridge, and the other Rogowski coil couples to the DC minus. So we're measuring then with two Rogowski coils the DC plus current as well as the DC minus current. A downside of that approach is it's fairly large in size. So each Rogowski coil itself has a footprint of approximately 7.3 centimeters square. And then the total size for current sensing that we just need for the Rogowski coil is 14.6 centimeters square. And the question was, how can we decrease that, the size itself? And how are we able to decrease the components, the passive components we need for the integrator circuit? And that was then the idea of using the Planar Rogowski coil. It's fairly simple. Instead of using two Rogowski coils, we just use one. And we couple then that Rogowski coil to the DC plus as well as to the DC minus. That allows us then to reduce then the effective size that we need by half, but we also only need one integrator circuit, so we can reduce then the amount of active components, op amps, reset switches that we need. And CPES has published work on the current sensor, Planar Rogowski coil, in 2004 by Dr. Van Wyck. And we can utilize that same concept that they proposed in 2004 to create then the current sensor that is depicted then in the bottom left. So how does a Planar Rogowski coil work? Instead of having the Rogowski coil wound around the current carrying trace, the Rogowski coil is placed adjacent to the current carrying trace, but it's not wrapped around. So we have then, what I'm showing here in the top left is the side view of a Planar Rogowski coil, where we have then the DC bus trace, where the current flows then from left to right, and highlighted in orange, we have then the Rogowski coil windings. If we then take a cross-section of that view, we see then, again, the DC plus trace, as well as in the Rogowski coil windings. as there's current flowing through the DC bus trace, we induce a magnetic field around that current carrying trace. And we're able to measure that magnetic field, and it's changed then with the Rogowski coil windings. When it comes to the magnetic field, we see that it drops off, or it's very small outside of the DC bus width. Then once we enter then the area of the DC bus, we have then an almost constant magnetic field or flux density, and then it drops off starkly again as we then leave the current carrying trace. It needs to be noted that the Rogowski coil is open-ended, so we will only be able to measure the magnetic field where we have Rogowski coil windings. And wherever else there's magnetic field, we won't be able to measure that. And that has an impact on the sensor design itself. And for the Rogowski coil to work, as we have then the second DC bus trace at the bottom, the one condition that we always have to fulfill is that the direction and the slope of current change is not equal through the two traces. If it is, the magnetic field will stay constant even though we have a change in current, and we won't be able to measure that. So that is one condition that we always have to fulfill. When it comes then to the Planar Rogowski coil, again we have then two coupling to one coil, where we have the mutual inductance MDC plus and MDC minus that couples then to the Rogowski coil. And the output voltage of the Rogowski coil is then the summation of the change in current through the DC plus times then the mutual inductance to DC plus, and then the change in current through DC minus plus, times then the current or the mutual inductance to the DC minus current carrying trace. That creates then unique operating states. We have in total three. We have the continuous conduction, the short circuit event, and the switch transient. And each of these operating states has an impact on the output voltage of the Rogowski coil itself. If we first go into the continuous conduction, how we define continuous conduction is that either the current, or that either the high side MOSFET or the low side MOSFET is conducting, but they are never conducting at the same time, which means that then the load current, I load, flows then through the DC plus trace if the high side MOSFET is conducting, or if the low side MOSFET is conducting, the load current flows through the DC minus trace. That gives us then the equation for the output voltage of the Rogowski coil, which is then either dependent on the first term, if the high side MOSFET is conducting, or then dependent on the current change through the DC minus trace if the low side MOSFET is conducting. That changes if we have a short circuit. In a short circuit, the high side MOSFET and low side MOSFET are conducting at the same time. We don't want to have that, yet we have to measure it and detect it in case it happens. If it happens, we see a large inrush current from the DC link capacitor through the DC plus trace, and that current then continues to flow them back to the DC minus trace. We have a short in our system. In that case, the current through the DC plus trace equals the current through the DC minus trace. So we can simplify the equation for the output voltage of the Rogowski coil by summing then the mutual inductances together and multiplying that then with the change in current through the DC bus traces. Then lastly, we have the switch transient. And the switch transient itself might not be as obvious in the beginning, so I'd like to use an example to explain then how the switch transient impacts the output voltage of the Rogowski coil. So what we see here again in the right, we have in the beginning until the time period T1, 150 ampere of current flowing through the DC minus trace, highlighted in green, which means the low side MOSFET is conducting. And then we have the switch transient, where the low side MOSFET will then start to open. And we see that then in the decrease in current then through the low side MOSFET. What happens then, as the load current is usually conducted, or the load is connected to an inductor, that current is constant. And as we decrease the current through the low side MOSFET, the current has to flow somewhere. And it chooses the path to flow then through the high side diode or body diode, meaning then that we see the same change in current, the dIdt, at the same time through the DC minus trace as well as through the DC plus trace, which means that the equation that we had for the short circuit event is also true then for all switch transient events. Now that we have outlined the operating principles of the Planar Rogowski Coil, I'd like to dive then into the current sensor design itself. What I'm showing here in the top left is a half-bridge PCB, where we have then in the top left then the DC bus connections. At the power connections, we have our decoupling capacitor and the 1.2 kV silicon carbide MOSFET half-bridge. We have placed then the Rogowski coil between the decoupling capacitor and the half-bridge itself, so its location will be here. If we then hide the FF4 structure and zoom into the trace layout, you see that the PCB or the Rogowski coil design itself is fully done within the PCB structure itself. So we utilized in PCB traces and the via structure to create then the Rogowski coil. For better visibility, I'm then displaying then the same Rogowski coil sensor in an exploded view in the bottom right, where we have then highlighted in yellow brownish the DC minus trace, and then at the bottom we have then the DC plus trace. In between, again created then with traces and vias, we have then the Planar Rogowski coil, where it doesn't circumvent the current carrying trace, it's just placed adjacent to the current carrying traces. And the winding itself, depicted in the top right, is then created with vias, where you have then the right part of the winding is then created with vertical via. We go then forward slightly, as we have limitations in space, and then go up with a laser drilled via. So that creates then the right vertical structure of the Rogowski coil winding. Then we use the traces to create then the top horizontal structure. Use the laser drilled via again, go forward and go back down. That creates then the left column of the winding itself. And then we use then again a trace structure at the bottom to create then the full winding of our Rogowski coil. What you can see within the PCB that we extend the winding or the Rogowski coil by one winding beyond the DC bus structure. I'll go into the details why we do that later. But what we also see is that the design sensor has a size of 1.06 centimeters square. That's 14 times smaller compared to the helical Rogowski coil. So the Planar Rogowski coil has good possibilities of decreasing the size itself of the sensor. When it comes to the sensor design, we had multiple options. One would be, what I'm showing then in the right figure, is then to have a Rogowski coil that doesn't span over the whole width of the DC bus. Second version would be then where the Rogowski coil spans over the whole width. The impact of the Rogowski coil length itself becomes visible when we look at the current distribution within the DC bus. If we assume we have a 30 millimeter wide bus and the current is equally distributed, what happens there is that the flux density induced by the DC bus current is fairly or nicely distributed over the whole width. There, a short-centered Rogowski coil as well as a wide Rogowski coil would be able to measure then the flux density change nicely. What happens or what can happen is that the current is not equally distributed within the DC bus itself. What could happen is that the same current now is crowded in the left third of the DC bus. If we then look at the area where we have the short-centered Rogowski coil, we see that there's only a small flux density within that area, meaning that the Rogowski coil would not measure the correct current. Yet a wide Rogowski coil will be able to measure the large peak in flux density when it's shifted to the left. Because of that, it's preferable to have then a Rogowski coil that spans over the whole width of the DC bus. We even go further and say that it's better to have then multiple windings than exceeding the DC bus. We use then ANSYS Q3D simulations to prove that claim. What we see in the left then is the simulation 3D model that we used, where we have then in red the DC bus with a DC bus width of 13.5 millimeter. And then we had then multiple iteration steps where we decreased then the size of the DC bus and then had the current crowd into a more and more narrow area within the DC bus structure. But we kept the current the same. to then emulate current crowding. Then we measured then, or simulated what the mutual inductance drop is as the current crowds then towards the edge. And we see that the mutual inductance, which defines the output voltage of the Rogowski coil, decreases as the current crowds towards the DC bus edge. And you want to keep the mutual inductance constant over the whole measurement range. You can improve that by adding one additional winding that exceeds the DC bus structure, that adds then 1.5 millimeter to the whole Rogowski coil length itself. But adding that one winding helps with the current crowding, that the mutual inductance doesn't drop as much. It actually decreases the drop by 76%. If you add the second winding, so you extend them by 3 millimeters, you see that there's still a small drop, but it's starkly reduced. It's actually reduced then by 94%, the error. So we recommend then, when designing a planar Rogowski coil, to have then at least one winding that exceeds the DC bus structure. We've tested then that as well and emulated that. We have then our half-bridge prototype with the top view, again with the decoupling capacitor, our silicon carbide MOSFET half-bridge. And we have then two PCB structures. We've taken X-rays of the top view of that PCB structure, where you see then the Rogowski coil windings, and are highlighted in red then the DC bus structure itself, where we then in the first image have then a white DC bus, and in the second image we have then the current crowding towards the right side. So I narrowed down the DC bus. And then in the measurement results we see then what impact that has on the switch transient current measurement. It also brings us then to the experimental results. We first evaluated the bandwidth of our Rogowski coil. The bandwidth is defined or impacted then by the self-inductance of the winding, the series resistance of them, as well as then the winding capacitance. For measuring, we connected then the PCB directly with an MMCX connector to an impedance network analyzer, not impedance analyzer. We use the network analyzer because it has a much higher bandwidth of 2 gigahertz, and we do need that bandwidth, as we see then in the output impedance measurement results. We see that the peak of our planar Rogowski coil is at 283 megahertz, and that is also the maximum bandwidth that we can achieve with our planar Rogowski current sensor. Comparing that to helical Rogowski coils, we're by a factor of 2.5 higher compared to the latest helical Rogowski coil designed by CPES. We've then also evaluated the switch transient accuracy of our planar Rogowski coil, and we compared it to a commercial Rogowski coil. And we carried out double pulse tests. What you'll see that the planar Rogowski coil will reset before each switching transient. So then for the turn off switching transient, I applied an offset to the planar Rogowski coil so that we can see the overlap. But what's important is in the amplitude itself of the switch transient. What you see then in the top left is then the turn on switching transient of our planar Rogowski coil, where we had the double pulse test measurements at 600 volts and a current of 60 ampere. Also, the switch transient time itself was fairly small, or large, my bad. So we have a DVDT of minus 5.3 volts per nanosecond and a small DIDT of 0.39 ampere per nanosecond. What you can see is that the planar Rogowski coil as well as the commercial Rogowski coil, the current measurement overlaps almost perfectly. So we're able to match the amplitude as well as the actual switching transient with our planar Rogowski coil. It looks a bit different for the turn-off transient. The reason is, if you compare the DVDTs, we switch much faster, now at 31.2 volts per nanosecond. And we see then a difference in DIDT between the planar Rogowski coil as well as the commercial Rogowski coil. The planar Rogowski coil has a DIDT of minus 5 ampere per nanosecond, whereas the commercial Rogowski coil has a DIDT of minus 3.9 ampere per nanosecond. We so far still have to evaluate the reasoning behind that. Our guess at the moment is that due to the bandwidth limitations of the commercial Rogowski coil, which is capped at 30 megahertz, the commercial Rogowski coil is not able to measure very steep switching transients, whereas with the planar Rogowski coil, where you're able, as we have a much higher bandwidth, to capture them more better. Then lastly, we have then also compared then the impact of the current crowding within the DC bus on the switch transient amplitude. So we have then two PCBs, one with a narrow DC bus and then one with a wide DC bus. We kept the same current for both measurements. When you see that then also in the amplitude. What I'm displaying here is so we have carried out two measurements. What you're seeing here is the commercial Rogowski coil itself. So there you can see that the amplitude and the current for both measurements is the same. Now, how does narrowing the DC bus impact the amplitude of our current measurement? You see that is highlighted in blue, and we overlap that then with the wide DC bus structure in yellow. You see that the amplitude itself is matched nicely, meaning then that even now if we have the current crowding to in 5 millimeters at the outside of our DC bus structure, the piece or the planar Rogowski coil is still able to measure it accurately. That also brings me then to my last slide, the concluding remarks. What we've shown so far is that the planar Rogowski coil is able to accurately measure the switch transient. The unique placement of the Rogowski coil within the DC bus structure creates some different sensor gains depending on the operating states. The maximum bandwidth of the Rogowski coil is at 283 megahertz, which is 2.5 times higher than of comparable helical Rogowski coils. When it comes to the sensor size, we're able to decrease it by a factor of 14. And as we now only have one Rogowski coil, we also have only one integrator circuit. So that allows us to decrease then the amount of active components by half. That would be all from my side. I will show also a live demo of the planar Rogowski coil then during the lab dialogue session tomorrow, as well as going then into the integrator stage of the planar Rogowski coil current sensor. Thank you. Thank you for your attention.
Okay, so due to the time limit, can we have just one question, please? Yes.
Two quick questions. You use the two quick. you say in your summary slide where you said your Rogowski coil can get a bandwidth 280 megahertz. Did you calculate or you experimentally verify that? And the second one is the measurement is highly dependent on the mutual inductance, the I. If the current is flowing at different locations, supposedly you have different I. And how you compensate that?
Yes. Yeah. In respect to your first question, the 283 megahertz, that is measured. That's measured based on the output impedance of the planar Rogowski coil itself. There's a caveat to it. You have the current sensor is created by the Rogowski coil itself, and then you have the integrator circuit stage that comes behind the Rogowski coil. And so far we are able to achieve a very high bandwidth with the Rogowski coil, yet our integrator circuit stage, there we are limited by the bandwidth of the op-amps. So there we achieve a bandwidth of 120 megahertz. So the overall current sensor bandwidth is at 120 megahertz. We would be able to go up to 283 megahertz if we would be not constrained by the integrated circuit stage. And your point that you made in respect to the mutual inductance, you want to keep that as constant as possible for all operating states and also for all current crowding conditions. And that's what we try to achieve with, let me try to find that slide, with extending the Rogowski coil windings then beyond the DC bus structure. So as the Rogowski coil windings can only measure the magnetic flux density change where you actually have the windings, you can decrease the impact of the current crowding onto the mutual inductance by extending the windings then beyond the DC bus. So if you add then, for example, 2 windings, you see that then even though you have current crowding, the mutual inductance, it still drops, but by not much. It stays almost constant, so that's the yellow line. And you can achieve that by having then 1 or 2 windings then beyond the DC bus structure.
Thanks, Matthias, again.
Thank you.